Okay, so let us continue with game theory. So we will, in today's lecture, we will study a small game. It's a two-person zero-sum game where each player has two strategies, and we will show that Nash equilibrium always exists in two scenarios. If there is a saddle point, then there is a Nash equilibrium for pure strategies, and if there is no saddle point, then there is a Nash equilibrium for mixed strategies. So mixed strategies, as you may recall from the last lecture, is a strategy where you do not really keep on playing with the same strategy, but randomly choose between the two available options of strategies at every round of the game. So its mixed strategy refers to a random mix of the available strategy options. And as I already mentioned in a recent announcement sent out on Luminous, that so these arguments in regarding our proof of the Nash equilibrium always existing in these two cases that we will discuss in today's lecture is for your enrichment and your knowledge only, and these arguments will not be tested in the exam. So this is a special case of the Nash theorem, which is essentially it's saying that if you have in these sorts of games, you always have Nash equilibriums in appropriate in terms of appropriate kinds of strategies. So, for instance, here we see some examples. So, for in Nash equilibrium in pure strategies, or Nash equilibrium in mixed strategies, and so on. So, this is roughly an avatar of the famous Nash's theorem that we are going to do. So, we will discuss a small game. So, two-person zero-sum game with each player having two options, player 1, player 2, and the two options, let's call them two strategy choices, let's call them move 1 and move 2, and the payoff matrix is described as in here. And notice that since it is a zero-sum game, only the payoff for the first player is shown, and it is understood that the payoff for the second player is the negative of the payoff for the first player. Okay, so in terms of the payoff described as a tuple, this A, for example, corresponds to A for the first player and minus A for the second player. So and we can be more general here. So, for example, it can be a two-player game with n strategies. So, each player having n strategies. So, the payoff matrix will then be n by n, and it will look like this. Okay. So, Mij is the payoff for the first player when first player 1 employs strategy I and player 2 employs strategy j. So, so what can we say about this? So, so let us consider the following result. So, if M, this matrix M, has a so M is the matrix whose entries are Mij's. So, if this matrix M has a saddle point, then the saddle point is also a Nash equilibrium for pure strategies. Why? So, remember, so imagine that Mij is a saddle point. So, what can you say about Mij? What is the meaning of being a saddle point? It means that Mij is minimum in its row, that is row I, and Mij is maximum in its column, that is column J. Okay. So, these are the, so this is what it means to be Nash this is what it means to be a saddle point. Now, let's now study whether Mij being a saddle point should imply that Mij is a Nash equilibrium. Now, what is a Nash equilibrium? Nash equilibrium is a strategy profile, and we are talking about PO strategies here. So, it's a pair of strategies, one being employed by player 1, the other being employed by player 2, such that no player has any incentive to move away from this strategy. So, if the other player stays put in the current strategy, then the first player then the first player doesn't have any motivation for changing his strategy. That's what a Nash equilibrium is, right? So let's see if player 1 has any incentive for moving away from strategy I if player 2 stays put at strategy J. Now notice that Mij being a saddle point in particular implies that Mij is maximum in its column. So this means that, and what does the jth column of this matrix correspond to? Jth columns of the matrix corresponds to the payoffs for player 1 when player 2 uses strategy J. Okay? So jth column of this matrix exactly corresponds to the situation when player 2 is employing strategy J and player 1 can make any of the possible strategy choices between 1 and n. And Mij is precisely the payoff for player 1 when player 2 uses the strategy J and player 1 uses the strategy I. Now, what does Mij being a saddle point entail? Mij being a saddle point entails in particular that Mij is the maximum element in column J. So Mij is greater than equal to every other number which appears in column J. Now column J is precisely the collection of payoffs for the player 1 if the player 2 plays strategy J. So Mij being maximum in the column J implies that Mij is the maximum payoff which the player 1 can obtain if player 2 selects strategy J, right? So if the player 1 is playing strategy I and player 2 is playing strategy J and player 2 sticks to his strategy J, so we are only focused on the column J, jth column of the matrix, of the payoff matrix, then if player 1 via strategy I is maximizing his payoff. If he moves away from strategy I, his payoff decreases because Mij is a maximal element in the column, maximum biggest number in the column J. Okay? So this shows that if player 1 is playing I and player 2 is playing J, then if player 2 stays fixed at strategy J, player 1 have no incentive of moving away from strategy I. As soon as he moves away from strategy I, his payoff can only go down because Mij is the largest number in the column J. So let's now look at, so this was the analysis from the point of view of player 1. Let us now look at the analysis from the point of view of player 2. So player 2, so suppose both of them are playing, player 1 is playing strategy I, player 2 is playing strategy J. Suppose player 1, so we are analyzing the game from the player 2, he is considering whether or not to switch his strategy. And suppose player 1 stays put at strategy I, which means that the payoffs for player 2 are going to be given essentially by the negatives of the numbers which appear in the ith row, right? And then player 2, it makes sense for the player 2 to move away from strategy J to some other strategy J prime only if his payoff, the payoff for player 2 increases, right? Then only it makes sense to move away. So when the what is the, so if player 2 goes from J to J prime, his payoff changes from minus Mij. Remember, Mij is the payoff for player 1. So the payoff for player 2, because it's a zero sum game, is going to be minus Mij. So it's going to change from minus Mij to minus Mij prime, right? Now it makes sense for the, because player 1 is sticking to strategy I. So now it makes sense for the player 2 to make this switch from strategy J to strategy J prime only if his payoff increases. Now what is the condition? So payoff will increase if this, if Mij, if minus Mij, the current payoff is less than minus Mij prime, or Mij prime is less than Mij, right? But this is not possible, because Mij being a saddle point means that Mij is the smallest of all the numbers which appears in row I, and Mij prime is just another number in the row I of the matrix. So Mij being the saddle point immediately implies that if player 1 sticks to his strategy choice of strategy I, then it does not make sense for the player 2 to move away from strategy J to any other strategy J prime. So therefore both the conditions of Nash equilibrium are satisfied. If all the other players stick to their strategies, then there is no incentive for the remaining player to switch his strategy from the existing one, right? So that's exactly the definition of Nash equilibrium, and we have argued why a saddle point must be a Nash equilibrium. Okay? Any questions? So let us consider some remarks from player 1's point of view. For each strategy SI of player 1, what is the minimum payoff that player 1 can hope to win? So if player 1 plays strategy I, that means that we are focused on this row, and the minimum payoff is the minimum of the Mij's in this row, right? So it's the minimum payoff for player 1 if he plays strategy I is exactly the smallest number which appears in this row. So in other words, if player 1 plays strategy SI, then the minimum payoff which is guaranteed to win is the minimum of Mij, where J varies between 1 and n, so J varies over all the elements of this, all the numbers in this row. Okay? So minimum over J of Mij is the lowest guaranteed profit or payoff which the player 1 can hope to win if she plays strategy SI. And now an important quantity in game theory is when you take this minimum, notice that we have taken the minimum of a J, but still it depends on I, right? Because the minimum number in every row depends on which row you are considering. So now if you take a maximum of these numbers which depend, so these numbers depend on the row I. So if you take a maximum now among the rows of this minimal element in the row, then let us call this UR. So R stands for row. So this is the best possible guaranteed payoff for player 1. So the player 1 will be comparing strategies in the following manner. So I want a guaranteed payoff if for any particular strategy. So for any particular strategy, the guaranteed payoff is the minimum number which appears in that row corresponding to that strategy. Now I want to maximize this guaranteed payoff, which means that I should take the maximum of this guaranteed payoff over all the strategies, namely all the rows, which is exactly this max, this mean over J and max over I Mij. Notice that there is a certain order to this. You look at the Mij's and you first take the minimum over the J's, and then take the, after that take the minimum over the maximum over the I's, okay? Not the other way around. So if you do it the other way around, these things might not be the same. And the amount 1 might be actually larger if player 2 chooses his strategy unwisely. But in game theory, we usually never want to assume that the player 2 will make some mistake, and we always want to go for maximizing the guaranteed payoff or guaranteed profit. So now, so this was the analysis of the game from player 1's point of view. Let us analyze the game from the player 2's point of view. So suppose player 2 employs strategy Tj. So this is the strategy Tj. So what are the payoffs for player 2? Remember that the numbers appearing in this column, so this column is of course the relevant one if player 2 employs strategy J, but remember that the numbers appearing in this column are payoffs for player 1. And because it is a zero sum game, the payoffs for player 2, which we are considered in this discussion, which we are concerned about in this discussion, are the negatives of the payoffs for player 1. So the payoffs for the player 2 are minus M1j, minus M2j, minus Mnj. Okay? And he wants the first of all, he wants to calculate the guaranteed payoff, minimum guaranteed payoff when he plays strategy J. So that should be minimum over I between 1 and n, m minus Mij, right? So Mij is the minus Mij is the payoff when 2 is playing J and 1 is playing I. And then you want to find the minimum guaranteed payoff if player 2 for player 2 if he employs strategy J, and that's just minimum over I, minimum over the rows minus Mij, right? But notice that minimum of the negative of these quantities is just the negative of the maximum. Okay? Because if you take a bunch of negative numbers and you have their minimum, is just the maximum of these numbers with the negative sign in front. Okay? So this we will use again and again. If we take the minimum of a bunch of minus a bunch of numbers, then it is just equivalent to taking the maximum of this bunch of numbers and putting a minus sign in front. So this negative sign and minimum or maximum just switches when you change their order. So minimum of minus something is equal to minus maximum of those things. Okay? And similarly, maximum of minus some numbers is minus of the minimum of those numbers. So as soon as you have a minus sign and you switch it with a minimum or maximum, the nature of the minimum changes to maximum and maximum changes to minimum. That's what we will use. So from player 2's point of view, for each fixed strategy Tj of player 2, the minimum guaranteed payoff is minus maximum of Mij, where you take the maximum in the variable I, and this is the minimum payoff that she is guaranteed to win if she plays Tj. Now of course, this is the minimum, this is the guaranteed payoff if the player 2 plays strategy J. Of course, player 2 wants to maximize this guaranteed payoff, so she wants maximum of all the possible strategies, so maximum over J, which is the strategy of choice of player 2, of minus max 1 to n. So he's just maximizing this guaranteed payoff, right? And again, you use the same principle, you switch the minus sign out and change the nature of this maximum. So this is minus minimum 1 between j and n, and maximum 1 between I and n, Mij. Okay? So the quantity of interest for player 2 is this one. Notice the similarity of the quantity of interest for player 1. It's exactly the same thing, but with the order of the maximum and minimum switched. So we called it UR because R stands for the player 1, who was the row player. So player 1 strategies are being given by the rows. Similarly, this one will be called the strategy for this one will be called UC, where C stands for column, because player 2 strategies stand for the columns. And therefore, minus UC is by definition, so this is exactly minus UC, this calculation. So minus UC is the best possible guaranteed payoff for player 2. And the amount actually won might be larger if player 1 chooses a strategy unwisely, right? But as usual in game theory, we never want to assume that the opponent will make a mistake. So we always want to maximize the guaranteed payoff. So here is an easy fact. UR, the maximum guaranteed payoff for player 1 is less than equal to UC, which is the maximum guaranteed payoff for or minus UC being the maximum guaranteed payoff for player 2. So how do we do this? So remember that, so we will do it in the case of the 2-player game with 2 strategies per player. So remember that UR is just you take the minimum of the rows and then maximize, you take the minimum of each row and then maximize over the rows. And you see, you take the maximum for each column and then minimize over the columns. Okay. So here are some simple inequalities. The minimum of A and B is clearly less than equal to A, right? Because minimum of A and B is that if A is smaller than B, then it's A itself. But if B is smaller than A, then the minimum of A and B is equal to B, which is smaller than A. So in either case, minimum of A and B is smaller than A, less than equal to A. Similarly, A is less than equal to the maximum of A and C, because maximum of 2 numbers is always greater than or equal to both the numbers, right? Similarly, B, you can write down similar inequalities for B. So minimum of A and B is less than equal to B, right? Because you are taking, it could either be B or it could even be A if A is actually smaller than B. Similarly, B is less than equal to the maximum of B and D. Okay. So now, so this together implies that, so the minimum of A and B is less than equal to maximum of A and C. Minimum of A and B is less than equal to maximum of B and D. These together implies that minimum of A and B is less than equal to both maximum of A and C and maximum of B and D. Okay. So now, think of 3 numbers alpha, beta, gamma, such that, excuse me, so suppose we have 3 numbers alpha, beta and gamma, and alpha is less than equal to both beta and gamma. So then what does that mean? It means that alpha less than equal to beta and alpha less than equal to gamma. But this in particular means that alpha is less than equal to minimum of beta and gamma, right? If alpha is less than both beta and gamma, then alpha is less than equal to the minimum of the 2. So now apply this understanding to here. The minimum of A and B is less than equal to both the numbers maximum of A and C and maximum of B and D. So this implies that the minimum of A and B is less than equal to the minimum of these 2, which is the minimum of the max A, C and max BD. Okay? Which means that the minimum is less than equal to, so the minimum of A and B is less than equal to the right hand side, which is exactly this. Okay? Similarly, you can do an argument, a similar argument, and show that minimum of C and D is less than equal to the right hand side. But if two numbers again, alpha, beta, gamma, now such that beta is less than equal to alpha, gamma is less than equal to alpha, together implies that maximum of beta and gamma is less than equal to alpha. Okay? But the maximum, so these two inequalities together implies that the maximum of minimum AB and minimum CD is less than equal to RHS, right? But this is exactly the LHS. So UR is less than equal to UC. Okay? Any questions? So let us have some further discussion on saddle points. So if the payoff matrix M has a saddle point, then actually UR is equal to UC, and and if the saddle point is Mij, then the common value is Mij. Okay. So let's do it again in the two strategy case. So suppose A is a saddle point, then so imagine that this is a saddle point. So if this is a saddle point, then it is the minimum of a row. So in particular, it is less than equal to the maximum of the minimum of rows, right? So A star is less than equal to UR. Similarly, if A, since the saddle point is the maximal of a column, therefore the saddle point is bigger than equal to the minimum over all column maxima. Okay, so A star is bigger than equal to UC. So if you combine these two inequalities, you can express it as UC less than A star from here, and A star less than UR from here. But from the previous discussion, previous slide, we have UR is less than equal to UC always. So this is less than equal to UC. So on the left hand side you have UC, on the extreme right you have UC, and you have less than equal to signs. So the only way this is possible is that all the numbers in between are equal, and therefore UR is equal to UC is equal to A star, which is the value of the saddle point. Okay. Any questions? So okay. Now, so we just showed that if M has a saddle point, so we showed that if there is a saddle point, then UR is equal to UC, and in fact that's equal to the common value of the saddle point. The converse is also true, that if UR is equal to UC, so we already know that UR is always less than equal to UC. But this result states that if UR is equal to UC, so if equality holds in the inequality UR less than equal to UC, then M must have a saddle point. So this is also a yoga with these similar to the previous discussion, so I am not going through the details. Okay. So assuming saddle point exists, both players should play the strategy that contains a saddle point. But what will happen if M has more than one saddle point? Okay. So then it can be shown that the values of the saddle points must be the same. So in terms of the value of the payoff, it doesn't matter which saddle point the player chooses. So what is a quick way of showing that? So since Mij is a saddle point, therefore it is the minimum in its row. So this is less than equal to the question mark. right? Mij is a minimum in its row, so Mij is less than equal to the question mark. Again, since MKL is also a saddle point, MKL must be the maximum in its column. So MKL should be bigger than equal to the question mark. So this shows that Mij less than Mk. Similarly, now you argue with MKL, start with MKL. Since MKL is a saddle point, it must be the minimum in its column. So MKL is less than equal to this question mark. And since Mij is also a saddle point, it must be the maximum in its column. So Mij is greater than equal to this question mark. So if you combine this chain of inequalities, MKL should be less than equal to Mij. So the only way this can happen is that these two are equal, and since these two question marks are actually sandwiched between Mij and MKL, they are also equal to the common value. Okay? Any questions? Okay. So here is another little fact which holds for 2 cross 2 matrices, but it might not hold for bigger matrices. So suppose the matrix M has a saddle point. So it can, for 2 cross 2 matrices, it can be shown that having a saddle point is equivalent to having a dominated row or a dominated column. So what is a dominated row or a dominated column? So let's say the row AB, we say that the row AB dominates the row CD if entry wise there is inequality. So if A is so if A is bigger than or equal to C and B is bigger than or equal to D, so entry wise there is domination, we say that row AB dominates row CD. Similarly, you can consider domination of columns where where the dominant column is bigger entry wise than the corresponding entry of the not dominant column, okay, of the other column. So, and saddle point is there if and only if there is a dominant row or a dominant column. And again, the argument for this is also similar to the yoga we have seen before. So essentially you just use the definition of the saddle point and the definition of domination and chase these numbers. Okay, so I will not be going through the yoga once again. So so we have already seen that if there is a saddle point, then the saddle point is a Nash equilibrium. Okay. So now let us think of the situation where there is no saddle point, and if there is no saddle point, then we discussed at the beginning of the lecture, then we will look into the possibility of Nash equilibria in mixed strategies, not pure strategies. Okay. So let's see how that works. So so suppose this payoff matrix has no saddle point. So of course in that case UR must be less than UC, because if UR was equal to UC, then you would have had saddle point. So UR is less than UC, and if UR is less than UC, there is no Nash equilibrium in pure strategies. So we want to show that instead the payoff matrix M has a Nash equilibrium in mixed strategies. So how do we do that? So we do the analysis step by step. So since we are looking at mixed strategies, we have to bring in probability. So the first player 1 chooses strategy 1 or strategy 2 with probability P and 1 minus P respectively. Similarly, player 2 chooses strategy 1 or strategy 2 with probabilities Q and 1 minus Q respectively. And then now the question is, what mixing parameter P and Q do they choose? And the question is boils down to the optimal choice of the parameters P and Q. Okay. So so let's now write down the payoffs. First, from the player 1's point of view, if player 2 plays T1, which is this column, player 1 and player 1's mixing parameter is P and 1 minus P, then if player 2 plays strategy 1, then the expected gain for player 1 is A times P plus C times 1 minus P, which you can simplify as A minus C times P plus C. Similarly, if player 2 plays T2, so then player 2 could either choose strategy 1 with probability P, strategy 2 with probability 1 minus P, the payoffs are B and D respectively. So the expectation is simplifies to B minus D times P plus D. Okay. So these are the possible strategies, these are the possible expected gains, and the guaranteed expected payoff for player 1 when she mixes strategies with probability P is a minimum of these two. Okay, because player 1 doesn't know whether, so A minus C times P plus C is the player 1's expected payoff when she mixes with parameter proportion P, and B minus D times P plus D is her expected payoff when she mixes with parameter P when player 2 plays strategy 2. Now player 1 doesn't know whether player 2 will play strategy 1 or 2, so she should prepare for the worst, which is to take the minimum of these two expected payoffs. Okay, and her goal would be to choose P such that this minimum expected payoff is the biggest in terms as a function of P. Okay, so this minimum expected payoff is a function of P, and our goal is to choose P, the optimal value of P, so as to maximize this function of P. Okay. So now, so this is the thing. So we have this payoff matrix A, B, C, D, and we are studying A minus C times P plus C, B minus D times P plus D. Now at some point we have to use the fact that there is no saddle point. If there was a saddle point, then it would have been very simple, and we could have had Nash equilibrium in mixed strategy, in pure strategies itself. Now we are working under the hypothesis that there is no saddle point, and somewhere we have to use it. And the way we use it is to invoke the little result which we discussed a few slides ago. So basically, for 2 cross 2 matrices, there is a saddle point if and only if there is a dominated row or a dominated column. Okay, so this means, so this is an equivalent. Remember, if and only if. So it is equivalent, right? So now, so this means in particular that if you are told that there is no saddle point, then there must not be any dominated row or any dominated column. Okay, so what does that mean? How can we use that? So that means that if you take the two rows A, B and C, D, then the statement that there is no dominated row means that if A is bigger than C, B has to be smaller than D, right? Or if A is smaller than C, B has to be bigger than D. Both inequalities cannot go in the same direction. Okay? So this is how we are going to, so the fact that there is no saddle point immediately implies certain kinds of inequalities between the entries of the matrix. So that's what we are going to use. So since we don't have dominated rows, we must have A minus C and B minus D of opposite signs, right? Because A minus C basically is positive if A is bigger than C and negative if A is smaller than C. Similarly, B minus D is positive if B is bigger than D and negative if B is smaller than D. And there is no dominated row implies that it cannot be simultaneously true that A bigger than C and B bigger than D, or A smaller than C and B smaller than D. These things cannot be either of the two possibilities, that these inequalities go in the same direction cannot be true together, right? So this means that translated in terms of A minus C and B minus D, this simply means that A minus C and B minus D cannot be of the same sign. So they have to be of opposite signs. So let us assume that one of them has to be positive, one of them has to be negative. So let us assume that A minus C is positive and B minus D is negative. So this means that C is smaller than A. Oh, wow. This means that C is smaller than A and B is smaller than D. So C is smaller than A and B is smaller than D. So the inequalities are going in the opposite direction so as to ensure that there is no dominated row. Now, let us look at the relationship between C and D. If D was smaller than C, then remember we already have C smaller than A, and if D was also smaller than C, then we would have had, C was smaller than A from here, okay, C was smaller than A, and if D is smaller than C, then D, you will get this inequality, and we already have D is bigger than B from here, so you can append them. But if you have this kind of an inequality, A bigger than C bigger than B, D bigger than B, then you notice that A is bigger than B and C is bigger than D. So if D less than C was true, then the column AC would dominate the column BD, which is also not allowed, because since you do not have saddle points, then by that equivalence by that equivalence theorem, that there is no saddle, that there is a saddle point if and only if there is a dominated row or a dominated column, means that in particular if there is no saddle point, there is no dominated column. But if under these circumstances, if D was smaller than C, then the first column would dominate the second column. So because there is no saddle point, this is not allowed. So D cannot be smaller than C, so this implies that C has to be bigger than D. C has to be smaller than D. C has to be smaller than D. So we have B less than D, this is okay. C less than A, this is okay, and C has to be less than D. Okay? So these are the relationships with the tick marks are the okay relationships. And by a similar argument, using the fact that there is no dominated column, you can also show that B has to be smaller than A. Okay? So B is smaller than A. So these are the four relationships which you can deduce among the different parameters of the matrix, simply using the fact that there is no saddle point, and using the fact that for 2x2 matrices, existence of a saddle point is equivalent to having a dominated row or a dominated column. So now let us get back to this quantity VRP, which we want to maximize as a function of P. So this was VRP. So let's think about this as a function of P. So now notice that A is bigger than C, so this is positive, and B is smaller than D, so this is negative. So just like we had in the last lecture, so let's go up, we had this kind of a picture for the example in our last lecture using the game of tennis. We have a repetition of the similar kind of scenario here in the general setting. So basically this means that if you just consider this expression as a function of P, it is just a straight line with positive slope. It is increasing with P. If you consider this function as a function of P, this is a straight line but with a negative slope, so it is decreasing in P. and P is varying between 0 and 1. Okay? And notice that by these inequalities C less than D and B less than A, we have ensured that the increasing curve starts below the decreasing curve and the decreasing curve ends below the increasing curve. So, the decreasing curve or the decreasing straight line starts above the increasing straight line and they switch order at the end when P. So the decreasing curve starts above the increasing straight line for P equal to 0, and by the time P has increased to 1, the increasing curve, the positive slope line, has beaten the decreasing slope line, the negative slope line or the decreasing straight line, and has ended up above the negative slope line. So these are continuous curves, and if they switch their order, then in the middle they must intersect. So there must be a point, a value of, and a corresponding value of P star where they must intersect. And this P star you can calculate by simply setting A minus C times P plus C equal to B minus D times P plus D, right? This is exactly the intersection point. And the P star will turn out to be this simple algebra, and the value of P star, which is VRP star, will turn out to be this. Okay? So VRP star we will call as VR, and this is the best guaranteed expected payoff for player 1. Okay? So again, for every possible strategy by the opponent, we calculated the expected payoff. Then we took the minimum of these expected payoffs because we do not know what the other player will choose. So we just assume that he is playing adversarially, and we just take the worst case. So we take the guaranteed expected payoff, and then, but this guaranteed expected payoff, we still have one weapon in our hand. We still had one weapon in our hand, which is the tuning parameter P, which we could choose to mix our strategies. So this guaranteed expected payoff still depended on P, our tuning parameter, and then we cashed in on the fact that P was a tuning parameter and maximized this guaranteed expected payoff in terms of P, so as to find the optimal value of P, which is P star, which is what we discussed here, and thereby obtain the maximal guaranteed expected payoff for player 1. Similarly, you can do a similar analysis from the point of view of player 2 and get two other straight lines for player 2, one of them increasing slope, one of them decreasing slope. Observe that the conditions on the entries of the matrix, following from the fact that there is no saddle points and therefore no dominated rows or columns, ensures that the increasing straight line starts above ensures that the decreasing straight line starts above the increasing straight line for P equal to 0, and by the time the parameter P has here is the parameter Q. So for Q equal to 0, the decreasing straight line is above the increasing straight line due to the constraints imposed by the no saddle point condition. And by the time the parameter Q has increased to 1, the increasing straight line has beaten the decreasing straight line and they have switched positions. So they must have met, they must have intersected somewhere in between, and this somewhere in between point gives you the optimal value of Q, which is Q star, and the best value of the game for player 2, which is VR of Q star. And so similarly, by equating these two straight lines and solving for the parameter Q, you will get the optimal value of Q star, which is D minus B over A plus D minus B minus C. And you can also find the optimal value of the game, the best guaranteed expected payoff for player 2, which is AD minus BC over A plus D minus B minus C. And you might notice that this is exactly equal to the best expected payoff for player 1, which is not surprising because it is a zero-sum game. So the best expected payoffs should be the same. And so minus VC is the best guaranteed expected payoff for player 2. So the conclusion is that if you choose P equal to P star and Q equal to Q star in the manner that we discussed, then we get there is a Nash equilibrium of this small game of mixed strategies with when you choose these particular P star and Q star as the optimal parameters of mixing. Okay? Okay, any questions? So if there are no questions, this is all that we have for today, and we will continue next week.